today's session, where we will have one talk by Professor Bernard Ghanem, who is a professor in electrical and computer engineering here at KAUST, as well as the deputy director at KAUST AI Initiative. He will give a talk today named Towards More Realistic Continual Learning at Scale. And the stage is yours.
Thank you. Can everybody hear me? Okay, I stand between you and dinner and a fun evening, so I will not have this last I'm guessing this is the last lecture in the workshop for today.
Yeah, it's the only one today, actually.
Oh, it's the only one today. Oh wow, I feel special now. So I'm not gonna take too much of your time. It's not gonna be very in depth really on the mathematics. I apologize, but it's about maybe a topic that you're not very familiar with right now, and maybe, I don't know, you tell me. But it's a very important one in machine learning. In the workshop title, there's statistical learning, right? So you're all familiar with the importance of machine learning and learning from data, of course, and how important deep learning is, and this recent hype about large language models, so-called LLM, ChatGPT, I'm sure you heard of, and all that. By the way, on that point, whoever here is at KAUST, still in mid-June, there's going to be a sneak peek for you guys only. The announcement hasn't come out yet, but there's going to be a campus-wide workshop on large language models, ChatGPT, basically awareness of what it is, what it can be used for, use cases on campus, and how it can make your work efficient, and the future of it, actually. That'll be in mid-June. The announcement will come out next week. Anyway, today's talk is not going to be about ChatGPT necessarily, but it's going to be about a topic in machine learning that's really picking up speed, and it's really more aligned with how we as humans learn from the world around us. Okay, and this topic is called continual learning. All right, so okay, before that, first slide after the title should be the people who actually do the work, and their names and their pictures. So if you see them on campus or elsewhere, you congratulate them for the great work that they've done. The team at KAUST, my lab, as well as my collaborators and ex-students, actually in Oxford and Meta and other places. So there's been a bunch of work in my lab on the front of on this forefront of continual learning, which I think is going to be very useful in the near future. What is continual learning? I'm sure you've heard of at least the left-hand side of the slide, which is static learning. So for example, your ChatGPT that they were trained on, right? They trained it on really a static data set, a humongous, what's bigger than humongous? Humongoid data set of almost every website, every document ever created till 2022. Okay? More or less, let's say. They were able to crawl that much data, and they trained a humongoid model itself with billions of parameters, and it does an amazing job and all that. Great. And then they trained it once, deployed it, and you can go and use it right now through API calls with OpenAI, and it's deployed in the world. Forget ChatGPT for now, that's just one example. What about examples of people in industry that want to use machine learning in industrial setups, in real life setups? You know, you want to recognize a particular fish underwater, right? So what do? As a marine scientist, you collect a bunch of images of fish, you label what species of fish each image contains, and then you train a machine learning model to classify what species of fish are in an image, right? You collect the data set, you annotate it, you keep it once, you train on it once, you take that model that's trained, you deploy it in the real world, people start using it, they're happy that you gave them such a great model that classifies fish species, right? However, as time goes by, as the distribution of how these fish may look like, or the setups in which they are imaged changes, the performance of that model that you trained once and deployed once gets worse and worse and worse and worse. All right? We as humans, we don't do static learning. So it's not as if we have this pre-built data set in our heads, We've let's say a divine has trained it for us, implanted it in our brains, and it's never updated ever. We learn through observations. Our observations are continually happening, and the model is continually updating. All right. So this is where, on the right side, the continual learning paradigm is different. You train continually, and you deploy continually, similar to how humans are really set up. So in this paradigm, you don't have a static data set. No matter how big it is, it's not going to be enough. No matter how big it is, it's not going to really represent the distribution of the data that you will see in the future even. Okay? So as the data, so instead of looking at data as a static data set, you should see it as a stream. It keeps on coming. And in that stream, the data distribution may or may not change. And actually, in many cases, it does change. The distribution changes over time. So you need to be able to continually adapt to whenever these things change. Because in static learning, the core concept here is that you want to build a model on a training set, which are instances of the data distribution that you will see and test, right? That's the whole point. And in order to be able to generalize to unseen data, this unseen data is assumed to be sampled from the same distribution that you got your training set from, right? But if you deploy in the real world and the data distribution is actually naturally changing, this breaks this assumption. And this is why the performance actually decreases over time as the distribution changes. So we've done a lot. Actually, the majority of all the things that made it into the news about machine learning and AI and the great stuff about it is based on some static learning, meaning that you accumulate a huge data set, you train a huge model and you train it in a smart way, and you deploy it, and it does amazing stuff, right? But this is great. It's a great achievement. It will not sustain what's going to come. All right. So we should be thinking about data as a stream, and therefore we should be doing continual learning. Oh, the battery needs to be changed. Okay. All right. So I think I've made the point that there's a difference between static learning and continual learning. And continual learning is more aligned with what we would want in the real world. We don't want to keep on creating static data sets all the time, deploy, and then once the performance goes bad, you go back and retrain from scratch. We want something that continually updates with the data as a stream. Let me give you an example that has nothing to do with computer vision, which is my core expertise. It has to do with building a language-based model to analyze tweets on Twitter to recognize misinformation. Misinformation, you've heard of it. There's a difference between disinformation and misinformation. I'm not going to get into that. So misinformation can be labeled as, is this tweet misinformed or not? Okay. And it's a yes or no kind of answer. So you want to build a machine learning model that takes into account a tweet, which is language, and outputs, is it misinformed or not? And that's very helpful in determining when misinformation happens in Twitter. And it's, of course, very important nowadays because you can create misinformation very easily nowadays. So it's good to have a misinformation predictor or classifier. So if you had built a static misinformation classifier based on tweet data up until 2018, and then comes a very big event 2019, which is COVID. I'm sure you've all lived through that. What misinformation meant before 2019 is different from what it meant in 2019. Some added misinformation that could happen, specifically about the COVID virus, which didn't really exist before. So your misinformation classifier would have performed very badly in 2019 on tweets regarding misinformation and COVID. 2020, a big event also in the world happened, especially in one country, the US presidential elections, and a lot of misinformation happened on that. Again, because of who the candidates were, and they didn't battle out before. Misinformation meant something different before 2020 regarding US elections, and therefore, if you built your misinformation classifier up until that time, it would have created issues. It would have made false predictions. 2021, about the vaccines themselves for COVID, again, the concept of misinformation, the distribution of what it means to be a misinformed tweet has changed, and naturally so. 2022, misinformation about the Qatar the World Cup in Qatar. Again, the first time in Qatar, first time in this region, misinformation came up, and your misinformation classifier would have done badly if it saw tweets, misinformed tweets regarding the World Cup that year. This is just to show you that this varying distribution idea for a particular class that you're trying to classify is natural. This is in the real world, right? This happens all the time. And so we have to be able to adapt to this kind of change in distribution. So we go back to continual learning and seeing data as a stream. So one might say, okay, you know what, you're making things too complicated, right? So we know how to do static learning very well. SL is static learning. And if you want to do continual learning, look, whenever new data comes in from the stream, what do? You just append it to that humongous data set that you had, you're accumulating over time, and then you train, right? Same thing, so you have a big data set, new data comes in, add to that big data set something more, train the model on the whole thing again. Now, that has issues, obviously. First and foremost, you're going to be accumulating a very large amount of data. That's number one, meaning that where you're going to store it, in terms of computational constraints, how are you going to train such a thing? ChatGPT took at least hundreds of millions of dollars of cost, but months of training on specialized hardware to train. So you can't just keep on adding a bit of more data onto this big data set and accumulate more and more data as you go and train from scratch over and over and over again. Another restriction here is data privacy. So if you're a Facebook or a Twitter, you're not allowed to store all the tweets all the time. Actually, some companies are mandated by law only to keep that data on their servers for 24 hours, 48 hours, a limited amount of time. You're not allowed to accumulate this big data set anyway. So this option is not valid, unfortunately, even though we're really good at static learning. So the other alternative is, and this is something we're really good at, is something called transfer learning. That means, let's say you trained a big model on one big data set, and then you have another data set which is not the same labels or the same kind of annotations, but it's kind of related. You take that model there and transfer it to this new data by fine-tuning, by tweaking the parameters a little bit to align it with the new data, okay, with the new labels. That's called transfer learning, fine-tuning. We use it quite a bit. Okay. Now, why don't you employ it here? Here, you don't, with the transfer learning, with the fine-tuning, you don't need to save and accumulate a bigger and bigger data set. All what you do is, let's say at time t, you have a model. In comes a new batch of data. You fine-tune the current model that you have on that data. Okay? That means you don't need to keep the previous data at all. You just, whenever a new batch comes in, you fine-tune on it. Then another batch comes in, you fine-tune on that. Now, what is the problem with that? And this is at the core of why continual learning is so hard. There's this phrase, this research challenge that's still at the core of continual learning that is an open problem still. It's called catastrophic forgetting. If you were to use this strategy of learning continually by fine-tuning on every new batch of data that you have, you would do very well on the new data that you fine-tune to. But you quickly start forgetting and doing poorly on the previous data. So imagine, this is not how humans work. It's not as if, okay, I'm going through the world, I'm observing the world, and after a year, I basically forget what I knew a year ago, right? Well, usually that doesn't happen, right? For the core things, we remember things that happened to us when we were 5 or 6 or 7 or in elementary school and whatever. So this catastrophic forgetting is a serious issue, and it's been demonstrated over and over again in continual learning. It is a serious problem. So therefore, you cannot do this sequential fine-tuning. A new batch of data comes in. If you just fine-tune on it itself without taking into account any of the previous data, it will do very well on the new batch of data that you have, but very quickly start doing very badly on what was there before. That's why it's called catastrophic, meaning very, very quick forgetting. You forget the past. And this is not what we want. We want something. So for example, going back to the misinformation example, we don't want to forget what misinformed types of tweets were like in 2020, 19, 18, 17. We want to accumulate all the distribution so far up until that point about misinformation. We don't want to forget it. We don't want to really become really good at detecting or classifying misinformed tweets about COVID vaccines and then forget about the elections or the virus or all the different types of misinformation that happened before. So this is a serious problem. And to be honest, there's been an explosion of papers on continual learning to target this specific problem. This is at the core of continual learning. How do you not forget? Okay. So there's many types of the various families of methods. I'm not going to go into the details of all, but I'll kind of give you a snapshot of what each one really kind of means. If you've ever trained a machine learning model, you know that there's a loss. You want to minimize that loss over the training data, and with some tricks or some theory or whatever, so it is able to generalize to unseen data. You have a loss, right? And that loss is usually a expected risk minimization loss, or expected loss of how well you're going to predict on the training data. When you're in this continual setup, when new data comes in, right, you can you want to train on the new data, right? You have nothing, you have stored nothing from the past, right? You only have the current updated machine learning model at time t. In comes a new batch of data. You can fine tune on that, but you add a regularization term in your minimization loss, such that it encourages that certain weights in the network don't change too much from what was before. So you kind of give these weights of the machine learning model, the parameters of the machine learning model, some kind of weights of how important they are in the forgetting process. People have used the entropy on certain class predictions and Fisher information, and there's a whole bunch of instances of this family. But this is what it means. Basically, you add to the loss a regularizer that encourages some of the weights not to change too much and some weights to change a lot to prevent forgetting. Other replay-based methods or memory-based methods, they allow you a small memory buffer. You can remember a very small amount of the past data. That's allowed. Small amount, right? So let's say 500 instances, data elements, or 1,000 data elements, and your data set is in the millions and billions, right? Something small. And now the problem becomes like, okay, what do you add to that buffer? How do you maintain it as new data comes in? Do you flush everything out and then add new stuff, or do you maintain something from the past? What do you do? How do you remove? How do you add to that memory bank? How do you use the elements in the memory bank to update your network weights? That's also a big family of methods. Parameter isolation methods basically say that as you're continually training on new data as it comes in, maybe you should stop training certain parts of the machine learning model and add more parameters as the data comes in. You isolate some, you add more as the data comes in. You have to figure out when the data distribution is changing. And once it changes, you kind of elect to add more parameters to attend to that distribution change, for example. That's a big family also of methods there. And then more and more papers are coming out all the time. That's fun, that's great, but I'm not here to advertise for the methods that have come up so far, because they're very nice, very well thought out in the setup that's been designed for continual learning nowadays. The purpose of this talk is to give you evidence that the current setup in which these methods are being developed and compared against and evaluated are really not aligned with what we want in the real world. And therefore, if we take any of those continual learning methods, apply it to a real application, for example, the misinformation problem from Twitter, it won't work. It's not aligned to what we want in the real world. And there's reasons for that. So, for example, this is to motivate this thing. So nowadays, these continual learning methods, the different families of methods that I talked to you about, they say that those ones that use a memory buffer, like a small memory to allow to remember a bit of the past, they think that's very important. And they don't care about how much time it takes to update the machine learning model on the new data coming in. Okay, and that is a risky business. And we have a paper that we're going to present next month at CVPR, our leading computer vision conference, exactly about that. Okay, I'm going to mention that in a bit. This is, I mean, the two papers that I'm going to talk a little bit about go to the idea of the current conventional setup for continual learning is not the right one, and we need to reconsider in order to be able to not go down a rabbit hole that leads to a place where at the end of the day it's not going to be deployable anything realistic. Okay, we want something like ChatGPT or building image classification or detector models that work on our phones. They actually work in the real world. This is what we want, and we want to do it continually. So we have to think about setups that are realistic, and not, for example, like apply assumptions or constraints that make the math work out well, but it actually is not realistic. We want to get away from that. We want actually something to work. You as mathematicians, I think, would understand that, right? We don't want to add assumptions just for the math to magically figure itself out. We want something to work in the real world. So all the methods that I mentioned before are what we call offline, or the majority of them are called offline continual learning. What does that mean? That means these methods, they assume something about the data stream. Some of them even assume they know when, they're told when the data distribution is changing, which in real world, that doesn't happen, right? So you're not going to have an oracle tell you that, look, the data distribution now is changing, this information has a new definition. This is not going to happen realistically. In addition to that, the majority of them, they assume that they can control the data stream. That means they can, for example, use time to update the machine learning model, right? And during that time, they tell the data stream, stop. I don't want any new data in the meantime, and I will finish, and I will, update myself when I want. And once I'm done, you are allowed to give me more data. Well, the real world is not like that. The data of the real world is like a hose, basically. It's like a fire hose. There's more and more data all the time, and the rate of data is tremendous. You cannot just control it. So we have another paper next month that we're going to present where it's about online continual learning. This is a realistic setup that shows that if you treat data as an actual stream that you have no control over, all the current methods that we saw before that are up to like state-of-the-art methods, they actually don't do that well, believe it or not. You see, so those state-of-the-art methods that were state-of-the-art in this conjured up setup, this conventional setup, which was a nice design for a particular purpose that makes the math or makes parts of the machine learning problem nicer to handle, is not really realistic to this fire hose continual learning setup. And therefore, this is a call to action that there should be more. This idea of computational expense should be put into the thought process for the future continual learning methods. Okay. Yes.
Hi, Bernard. Ro asked a question here. He's asking if continual learning is the same as data assimilation and can be seen as a filtering problem.
I don't know the exact lingo that you guys use. So the filtering problem, I understand. What is data simulation? What is the data simulation problem? What is that?
I think he's talking about common filtering.
Yes. So yeah, so common filtering, but at a much more complicated function. Yes. So yeah. So you have a particular loss that we know, and we want to update. We want to minimize continually. There is a data distribution shift. And so, like common filtering, for example, you kind of adapt to that shift as you go. However, You want to do this for very large deep networks on very large amounts of data that is partially observed, given to you. So not as easy. The theory is not as simple as in Kalman filtering or particle filters, for example. But maybe this is why I'm here. Maybe it's me reaching out to you, the smart mathematicians, to see if there's some kind of ideas that can be used here. Actually, there was one part of this talk which has to do with Nyquist theory. Well, I think it's like Nyquist theory, but sampling theory. You'll see later about like how much data do you need to sample from the stream, such that if you trained on that sampled data, you would get as good of a model as if you trained on the whole thing. So imagine Nyquist theory, but not for reconstructing signals, but for, you know, reconstructing a machine learning model. This is something that I've conjured up. I've pitched it to my students in my lab. Nobody wants to work on this because they were like, "What is this?" Nyquist is about is about frequency spectra and reconstruction of signals, and you know, we want to work on other things. But we'll see it later about sampling, and when computation gets into the way where you can't handle the whole data stream, you have to start to sampling from it. But how do you sample? And how do you sample in a way that is lossless in the machine learning sense, meaning your performance, not the reconstruction of the thing, but the performance of the machine learning model on unseen data, you don't lose anything. So yes, it's related. Maybe some ideas of that could be integrated into the continual learning setup that we have here. We're open to ideas, really. This is the Wild West right now. We're trying to organize the Wild West, the chaos, so that at least we have a realistic goal in mind. Once we set that, then we can think about real solutions to the problem. Because if your goal is not aligned to reality and you start going down a rabbit hole towards that, it's going to the progress that you do is not going to be realistic. You see, so, and then the whole community might be going down a rabbit hole that leads to nowhere. And the two papers I want to talk about here, and we have others, is to position the field in a more structured way that we have all the same goal, and a realistic goal at that. Okay, and anybody who wants to contribute, please. So you have a data distribution change, right? So filtering makes a lot of sense, right? There's other fields, some fields of digital signal processing that also take into account changing of distributions. Maybe we can integrate that into the setup. All right, so to set up what the continual learning, offline continual learning is, there's a stream S. It reveals. We have this really cool words. You reveal. It's like an oracle. The data stream reveals to you a batch of data, NT samples at different time steps. Okay, so now it's a stream, right? There's a time. There's an idea of time. At every time step, the stream reveals to you a set of image. It could be image or data label pairs, and they come from a distribution that could be changing. It doesn't have to be the same over time. If you are using memory-based methods, you have to choose what you add to the memory, what you don't, and then you update your model. That's parameterized by theta. You go from theta t to theta t plus 1 somehow, using the memory, using some regularization methods, using the current data that you have, the NT samples, but here you have a computational budget, CT. Right now, the majority of methods, CT is equal to infinity. You can do whatever computation you want. The memory is usually constrained, and this is what people have been focused on mostly nowadays. So they say that memory is very important. We should limit it because of two main reasons. It's motivated by the cost of memory. Memory is expensive, and therefore it makes sense to have the memory buffer be small, and data privacy. You're not allowed to save people's data. GDPR and other kind of privacy regulations hold, and therefore, you can't have a big memory buffer that includes all the data. Those are the two motivations behind why we should focus on memory and not computation. But here, let's dig deep into actually if that makes any sense. Does restricting memory size really cut costs? And we are of the opinion that it does not. Computation is much more of a cost. Here on the left, you see a bunch of images from very small to very big. If those of you who have dabbled with deep learning, you may have heard of SciFar or ImageNet. ImageNet in the usual data set is like 1 million images with 1,000 classes. ImageNet 21K is much bigger and has 21,000 classes. Okay, it's a much bigger ImageNet. Okay, so from small to big, if you take a continual learning method and you apply it to these data sets of increasing size, we estimate how much cost would you incur, dollar costs you would incur for the storage of the data set on Google Cloud. We just took a vendor. Not married to any vendor. It's just one vendor. This is how much it costs. You see that even for the very large ones, the ImageNet 21K, that's 400 gigabytes of data, it'll cost you about $10 to store that thing. Memory is actually not that expensive. But running even a small number of iterations, which 8,000 costs you $35. For the ones that require many more iterations, you get $100 versus 2 cents of storage. So you have from 5 to 100, 1,000 times more cost incurred on computation than on memory. So if you are saying that memory is really important because of its cost, well, then you should be looking at computation. It's much more expensive. So I don't think that argument holds water. The other one is about privacy. Well, if you look at prior art, if you care about privacy, you should know about this work. There's some really interesting work out there. One work, this is just one of them. It's basically, if I gave you a trained model, people are working on methods to reverse engineer the training set that trained model was trained on. I only give you a bunch of parameters of a neural network, a very large one. And they are showing that, yeah, I could reverse engineer the images or the data that this thing was trained on. There's actually a bunch of interesting papers on this. So it means that these very over-parameterized neural networks are actually so big that they're in some way or another memorizing the data itself in some form within its weights. Some really interesting work on that. So if you talk about privacy, well, if I gave you a model trained on this data and you think, oh, I'm data private because I'm not giving you the data, well, I could reverse engineer the network itself to get the data. There's even worse, it's not worse, but even other types of methods called inverse attacks, where if you gave me a trained model and an image or a data element, and you ask me, was this model trained on this sample? And there's papers on that too, to check whether something has been trained on the model or not. And this goes a long way towards this idea of machine unlearning. You've heard of machine learning. How do you machine unlearn? For example, if you know that a neural network was trained or a machine learning model was trained on a data set with your own data, and you go and make a case and you tell that whoever made that model, you need to remove my data from that neural network or from that machine learning model. So take that model. How do you unlearn your data from it? That's called machine unlearning. And this topic is related to that. How do you determine whether the data point, the sample was actually used in the training of a model? And there's papers on that. So this idea of the data privacy and really it doesn't hold water either. I mean, GDPR also said it forces you, you can't just, in the memory-based methods that actually have a memory buffer where you choose which ones to add, which ones to remove, GDPR will tell you that you don't, it's not up to you to choose which ones you keep and which ones you remove. There are regulations for this. So I don't think these privacy concerns either hold water for limiting the memory and continual learning. So because of this, we're going to go back to what offline continual learning is all about. And instead of focusing on number 2, we're going to assume memory is infinite. Memory is infinite. Okay? Don't care how much memory you will use, but you'll see that it's not really infinite. And we'll give a computational budget, CT. It means that when you're updating from theta t theta t plus 1, you incur costs. It could be time costs, it could be dollar costs, whatever, some kind of reasonable computational budget. All right. And now you might say that, okay, but how can I have infinite memory? What about privacy concerns? I can't, save the whole data of all the world and continually add to it. But if you add a computational budget, it inherently or implicitly restricts how much memory you can have, because updating theta t to theta t plus 1 is proportional, more or less, to the amount of data that you use to update it. So if you have a humongous memory bank, you're not going to be able to finish updating the model on the whole memory bank given the budget CT. So CT inherently or implicitly restricts how much memory you can actually have, but in an indirect way, not in a direct way. I'll tell you a little bit more about what this all means in a bit. Okay, so here are two plots that we've smoothed out, and lots of experiments and lots of time on the shared GPU cluster at KAUST were used to create these plots, these nice colorful plots, and I will try to digest them now. So ERM is expected risk minimization. This is the simplest continual learning method you can think of. Okay, it's basically you have a memory buffer that contains some elements of the past that you randomly remove things from it and randomly add to it. Nothing too specific. And you update theta t to theta t plus 1 using that memory bank, and that's pretty much it. Okay? Simplest method, ERM. Computationally, it is the simplest among all of them. Then there's distillation methods, which are much more expensive, sampling and FC correction methods. I'm not going to go into the actual methods, but ERM is the computationally simplest and was state-of-the-art 3 years ago when continual learning first came out. It's the baseline that you have to always beat in every continual learning paper that you publish. Okay, so as the time steps go by, meaning as more and more data is revealed to you, if you measure the accuracy of this method on all the data up until that time, and you plot it on the y-axis, this is the plot that you get if you have unrestricted compute, meaning CT is equal to infinity, which is the conventional setup. Okay? You are allowed to update your model as much as you want for as much time as you want, and you see that the distillation, the born in blue, is higher than ERM. All of them are higher than ERM. Why? Because it's the baseline. Everybody's beating it, right? So as the community, as the literature improves it over time, your curves are going to get higher and higher and higher, right? All above ERM. But if you restrict that budget, that computational budget, and allow for infinite memory, what do you see? You see that the red curve is on top of all of them. And this was very surprising to us, right? It means that these very computationally expensive methods, distillation, sampling, and so forth, if you restrict them with a computational budget, which is realistic, by the way, right? If you want to deploy this into Twitter or Facebook or an actual realistic application, there's going to be a computational budget. You can't have infinite budget. You're going to have a reasonable computational budget. And if you put a reasonable computational budget on these methods, you see the computationally simpler ones are actually better in terms of accuracy. So they forget less if you impose that computational limitation. This was surprising, actually. It means that it's a complete flip from what was there before. What does this tell us? It means that it doesn't mean that these methods are bad. It means that they were being designed for this setup, okay, which is unrealistic because it doesn't have a computational budget. And therefore, as more and more papers came out, there's improvement in this setup. But if you took these same methods and put it in a little bit different setup, you see that they're really not improving. People are proposing more and more computationally expensive methods to update theta t plus 1, and actually they're less and less able to be deployed in realistic scenarios. Because this is what's going to happen if you deploy it in a realistic scenario. You're going to do worse than the simplest method out there. So that's the surprising fact that kind of the crux of, well, there's other conclusions that we had, but this is the crux of it, right? This is surprising. This is why I got accepted, I think. All right, so that's about computational budget, and it's going to come up again when we talk about the realistic setup that we want to propose to the community, and it's online continual learning. The methods that we saw before that were compared, the paradigm that we saw before was offline continual learning. As I said, the methods control the data stream. They know, some of them know when the data distribution is shifting. Okay, this is not realistic. The realistic setup is an online continual learning setup, meaning you have no control of the data stream, the data is coming in, you have no control over it, and you don't know when the data distribution is shifting. You have to do all of that. You detect it if you want, you know, when the data distribution is changing, you want to update it in a certain way, it's up to you. But this is the realistic setup. And I think we all agree that this is the realistic setup. So the Twitter stream would be online, you have no control over it. It's there, do what you can with it, so that you don't forget and you do very well at, for example, classifying misinformation. Okay, so real-world streams can be fast-paced, they're very, very fast. And this is realistic, and this actually adds some constraints to how you're going to train your continual learning method. Let's take the Twitter example again. Let's say you have the Twitter stream is coming in, and you have an online continual learning method, whatever it is. Its job is to predict misinformation. Your online continual learning method, okay, on good hardware, can be updated, theta t to theta t plus 1, at a rate of 35,000 tweets per minute. It's not bad, right? So, you know, you're presented 35,000 new tweets. You go from theta t to theta t plus 1 in a minute, okay? So basically, if Twitter is going to implement this in the back end, you know, its rate is about 35,000 tweets per minute because of the computational expense of the method needed to update the continual learning model from theta t to theta t plus 1. It takes time to update. But what is the actual rate of the data stream? 350,000 tweets per minute. This is from a data source from 2022. Maybe it's higher now. So there are 350,000 tweets being uploaded every minute on Twitter. So there's a discrepancy in the rate of update of the model and the actual data stream. The data stream is 10 times faster than the model, i.e., the method is 10 times slower in updating than the data stream. Okay, this is a part of real world. This is real life. So what does that mean? If you were to do the conventional thing that people did do in continued learning is this. So here are the timestamps. Think of this green box as the data that the stream reveals to you, the batch of data. Okay, it comes in. Your model is f theta 0, right? At time 0. It takes that batch of data and it infers on it. That means it produces predictions on it. Okay, and this same amount of data is used to update f theta 0 to f theta 1, right? And then a new batch comes in. You use it to infer, and then you use it to update and train, and then you keep on going. But what do you see here? You see here that the training, the update of theta t to theta t plus 1, miraculously, you know, finishes by the time that the second batch came. And this is not miraculously, it's because it was designed in such a way that this method controls the data stream. I will not accept the second batch of data. Oh, I will only accept the second batch of data when my first batch is done training on. This is not realistic. The realistic setup is that, so you inherently assume that the stream will wait for your model to complete updating. This is not realistic. So what is the realistic setup? It's this. New batch, the first batch comes in. Let's say you have a data stream that is twice as fast as updating your model. So the first batch of data comes in, you infer on it, you predict labels, you use it to train. But your training update, you're going from theta 0 to theta 1, will take 2 units of time, not 1, 2 units. So there's a delay, right? And in that time, a new batch comes in. You don't have a new model yet. You don't have theta 1 yet. So what do? You use the old model, f theta 0, to infer on it, right? So you're using an old model, right, and not updated on the new data, to infer on the next batch of data. This is all what you can do because your model is still updating. Then it finishes, you know, updating. Now you get f theta 1. But again, there's a lag, right? So this one is fine, but then there's a lag after that. And so you're basically, if you look at the updates, they're actually twice as slow. That's an issue. Because if the distribution is shifting as you go, right, then there's a lag between your model update and the data stream. Now, this is when it's twice as slow, but in the case of Twitter, it's, what was it, 350 to 35, so it's 10 times slower. So you're missing 10 times. So in the time that it takes you to update once, 10 batches of data have gone by and you haven't touched them. And by the way, you can't just save them for later. There's no later. Data is a stream, so this 350,000 tweets per minute, this is all the time. So there's no like, okay, at night, I'm going to leave these things that I missed, and at night, I'm going to, cram them for an exam that I have. No, there's no night or day. You're always updating continually. The data is continually coming in. So if you miss it, you miss it. That's it. There's no coming back to it. All right. So in image terms, what this means is that if you have a method A and it's as fast as a stream, you get to see all the batches of images as they are and update on all of them as they go. But if you have something that's 2 times slower, sometimes you see the first batch with the flower here, but this part with the planes is not seen at all. So you don't see this batch of data that could include some interesting semantic information that's useful in updating your model. You don't see it at all. It's not included in your training scheme at all. So of course, what does that do to your model? It makes it worse, right? Because it's not able to see all the data because of its computational complexity. You see how computational complexity is affecting how much memory how much data you can process, and in the case of online continual learning, it affects really how much data you can see at any given time. So we have some numbers here to show on a particular task. This task is image-based geolocation. So what does that mean? If you take a picture of an image, especially outdoors, and you want to predict the GPS location, or you want to predict which region of the world it's coming from, that's an actual task. You can get lots of data from this because people who upload to Flickr, to Instagram, to whatever, there's a geotag. You don't realize this, but if you open up your iPhone and go to this the properties on your image, it gives GPS locations. And if you upload it, guess what? That company, that Instagram or Flickr or Facebook, whatever that has it, they know where that image was taken. So there's a huge amount of data being uploaded. So actually now you can take images that are uploaded, you know where, right? And based on that, you can build a machine learning model that can predict the geolocation based on an image only. And there's a data set out there. It's 38 million image location pairs. And we treat it in a continual learning way. That means we don't have all 38 million at the time. We're assuming that this data is being uploaded by users, so they're being uploaded sequentially. Okay, and you want to train on such a data stream. And here's kind of the timestamp. Time steps going from 0 to 300,000 time steps. And at every time step, you get a new set of images with geolocations, and you have to train on it. Again, the y-axis is how well you're doing. Are you forgetting or not? Higher, the better. And as you see, as the time goes forward, you get better and better, meaning that you are not forgetting the past as much, and you want to be at the highest plot. Okay. ER is the ERM method, the very basic method. Now it's in blue, and these are the more sophisticated methods. Okay. What do you see? They do the worst in this online continual learning setup. ERM is the blue. Again, it is the most computationally efficient, and therefore it is able to keep up with the data stream. So here we're assuming that we're simulating a setup where users are taking images and uploading, There's a certain rate, there's a certain frequency of the data stream revealing data, okay, organized in this time axis, and you're only allowed a certain amount of time to update your model as the data stream goes by. So if you're as fast as the data stream in updating your model, let's say ERM is, because it's very computationally efficient, then you see all the data. If you're twice as slow, then you do more complicated things, but on a smaller amount of data. That means you sample the data stream at a rate of 2, right? So you don't see the whole data, you see half the data. If you're 3 times as slow, you see a third of the whole amount of data, and so forth. You get the point. And so what this shows is that if you put these methods in this setup, it's better to see all the data and do something simple than it is to do something more complicated, meaning computationally complicated, on a smaller set of the whole data stream. So it's better to sample more aggressively, more densely, than it is to sample sparsely the data stream, no matter how complicated your update method is. So some of you might think this is unfair, because these complicated methods, right, they're doing worse because they're not seeing all the data, right? They're not seeing it even once. They're not seeing it at all. So again, a method that updates at the rate of twice the speed of the data stream, sees only half the data. So we did another experiment where, to be fair to these more computationally complicated methods, we say the data stream is as slow as the slowest continual learning method. Okay. In that case, the slowest continual learning method is able to see the whole data stream, right? Each batch, it can do, we do neural networks, right? We do deep networks. So when I say update theta t to theta t plus 1, we're doing gradient descent, basically. We're having the loss, you get the gradient on that new data, you update the weights to go from theta t plus 1. You do one iteration of update on the new data. This is what you do. Okay, so now in this setup, when you slow down artificially the data stream, the complicated methods can catch up. They get to see the whole data stream, and they can do one gradient step for every new batch of data that you see. Okay, but the computationally efficient ones like ERM, now it's like, okay, I've updated once on my new batch of data, and now I'm waiting because now I'm faster than the data stream. I'm faster, so I update and then I wait for the newer batch of data. We thought to ourselves, that's not unfair to ERM. That's unfair to ERM. What can you do in that time? You don't need to wait. What can you do? Instead of doing one iteration of gradient descent on the new data, guess what? You can do, if you're twice as fast as the data stream, you can do two iterations instead, or 3 if you're 3 times as fast, right? Because it's unfair to ERM that it's just standing there waiting for the new amount of data. No, you can do more iterations. You can use that computational budget. And guess what? In that setup, you get a similar plot. So it's not about seeing more or less data, because if you see the data once, you're not allowed an infinite amount of computational budget to do 1,000 iterations or an infinite number of iterations on it. You're given enough to do one iteration. That means you've seen the data only once. But if you are computationally efficient, you could see the data. You can update your theta t multiple times with multiple iterations using staying within the computational budget. You actually still do better than the computationally complex ones. That's very, very interesting. You get a similar plot to this one. So so before, people didn't think about that. Before, it was unfair to ERM. Even though it is faster than the data stream, it was you trained it in the same way as you did the complicated models. The complicated models are allowed one iteration, ERM was allowed one. That's not fair, because it's just doing one iteration of update and it's waiting for the next amount of data. But in that time that it's waiting, it could do other things. If it does more iterations of update, it can get better performance. So again, maybe the setup has to be reconfigured so it's more realistic. So the take-home message is, I hope I gave you empirical evidence that we should be looking at data as really a stream. It's continually coming in. It's not static. Okay? And the amount of time, the computational budget that your continual learning method requires is very important, and it has to be considered in any setup that allows us to deploy continual learning in the real world. And we're proposing a new kind of a benchmark, evaluation benchmark for online continual learning that's very realistic, right? In the realistic setups, your data is continuously coming in. For example, if you have IoT devices, if you have cameras up, Twitter is another example, Facebook, there's no stop to the data. You cannot just stop it and then I'm done. The data is always coming in, and you should always continually update from it. So if you set yourself up in that proposed framework, and you do not control anything about the data stream, you don't know when the distribution shifts, and you don't know, and you cannot stop it whenever you want, you have to deal with lags between the data stream rate and your update rate. And how does that affect things? So I mentioned to you about Nyquist. This idea of a data stream and then something being fast or slow is about sampling, right? It's like if you have a signal, 1D signal, that's what Nyquist is all about, and you sample from that continuous signal, how frequently do you sample from the signal so that you can reconstruct the signal in a lossless way? And you have to sample it at least twice the highest frequency of that continuous signal. That's what Nyquist told us, right? But then there's compressive sensing that tells us maybe you can do it at a less rate, whatever. But not with probability 1 for all signals, but with a high probability that it can be done. Regardless, this is similar. If you have a data stream, you're not trying to reconstruct data. You're trying to build a machine learning model to generalize well on a particular machine learning task with labels. But how often do you sample from this data stream? Do you need to look at every single data element? That's another, it's a question in continual learning, actually. Do you need to see everything? There's papers that say, no, you don't. If you choose wisely which data samples you update and which ones you use to update and which ones you don't, you can actually do something much more efficiently, and then you could keep up to the data stream, for example. Do you need to see all the data? There's a lot of redundant stuff coming out there. That's another kind of direction of research that people are looking into. And that goes to the idea of sampling, like how much do you sample? What we've shown, without a shadow of a doubt, is that the methods that exist right now in this online way, where data is a stream and you have no control over it, they're not sampling enough, right, to be able to have a good performance or less catastrophic forgetting. Just to let you know that the stuff that I've talked to you about is agnostic of the task. I talked to you about an image to GPS task, but really this, it's very general. It applies to any machine learning task, really. And of that specifically, you can have it applied to video tasks. So given a video, you want to recognize what are people doing in this video, right? Or you want to recognize where people in the video are doing particular things, particular activities, like abnormal activities, for example. With video, the sheer stream of video, so 80, I think the statistic is more than this, but the last statistic that I know from Cisco says that 82% of all internet traffic is because of video on the internet. The internet, all the internet. 82% of all packets are because of video. I mean, it's clear. We're on Zoom right now. I'm presenting here. I'm shooting out video packets. It's recording, so packets from the recording are being dumped to some server. You guys are doing, of course you're not doing any torrenting, but if you were, you're downloading, you're sharing peer-to-peer, you're streaming on your favorite streaming site. It's very easy to record video now and upload. You're sharing with each other and so forth. So 82% of the whole internet is video, and video is massive in terms of data consumption, right? So imagine if you had a memory issue in continual learning, it gets even worse if you take tasks that have to do with video. So because my background is in computer vision, we love video. We want to build the best models for video, and so we were the first to really see how would you train video machine learning models continually for the first time ever. And it is a very tough task, really, because of the sheer computational and memory limitations that you have. Companies like Facebook, Google, and Apple, and so forth, they're very interested in this because imagine YouTube. There's 400 to 500 hours of YouTube are uploaded every minute. That's the rate. 400 hours per minute. Training a machine learning model on video, trust me, is nowhere near that rate. So you would need probably hundreds of thousands of GPUs running at the same time to be able to sustain. Of course, you can always parallelize with hardware, right? So to keep up to that rate. But you would need hundreds of thousands, if not more, of GPUs to be able to sustain that rate. Of course, not a lot of companies have that. And do you need all that? That's the idea behind continual learning. Do you need to have 100,000 GPUs doing very computationally expensive things to update its model, or use a fewer number, but you do the continual learning updates in a smarter way? So you see there's real world implications here of continual learning. And it's a real thing, and it goes beyond static learning, what we're used to. So and these are just a couple of papers that we have on continual learning for video tasks. But this is a call to action, that this is a serious problem. This is a realistic problem. This goes beyond what we usually assume in static machine learning, which is the data distribution of the test set is the same as the training, because it could change. And I think it relates to a lot of the work maybe in data simulation, filtering, and whatnot. So there might be some symbiosis here, where you guys can benefit maybe from a new application field. We can benefit from ideas and theory from your end. But just to let you know that while people are looking at ChatGPT, and these are all, think of it as, these are the majority of them, the vast majority, I would say, not to say 100%, 99% are statically learned, trained machine learning models. That's why ChatGPT, now they're updating it, right? In a certain way, maybe with continual learning. But when ChatGPT first came out, if you asked it questions about 2023, it wasn't able to answer. Why? Because it didn't crawl 2023 yet. It was released in November 2022, so it crawled everything at least before that, right? At least by November and before. So you get the point, right? So you can't just keep on doing things statically. So it's a serious problem. It's a evolving field, and I think it needs multiple aspects of attack to be able to resolve it. And with that, I'll end. I'm right on time, not letting you ask any questions, but that's fine. If there's a few more minutes allowed, we can take questions now, and I'm here for that. Thank you.
Thank you so much for the very interesting talk. Yes, we have some time for questions.
Yeah. Hello. Thank you for the talk.
Thank you.
I just have a simple question. Like, if you think that at data at time t1, you have a distribution, right? Let's think of it that way. And at t2, you have a different distribution.
You may or may not, yeah.
Yeah, you may or may not,
Yeah.
right? Then you somehow have like a function that transforms this distribution in a sense, right? Can you use that function in order to change and to update the weights in a more efficient way, like calculating the gradient or whatever?
There are papers that are in some way trying that. There's papers that don't really use this to update the model parameters, but the data. So, you know those replay-based methods, the memory-based methods I talked to you about? That memory doesn't necessarily, it's like memory, number of bytes, right? It doesn't necessarily have to be samples of data that you saw in the past. It could be an abstraction of what you saw in the past. Have you heard of generative models? Have you heard of GANs, these diffusion models that generate really cool images? You could continually update a GAN or diffusion model based on all the data that's saw in the past, so that one model can be able to, you can probe it to generate all the past images or all the past data. And by doing that, you are subsuming the data distribution shift into those parameters. So your memory bank is not a memory bank of data samples from the past, but it's a memory bank of parameters of another network that's trying to estimate the distribution. And there are papers on that. But of course, it's an open field, really. And yes, this is exactly what you want to do. For the papers that are interested in determining when a distribution shift is happening, there's papers that they detect the distribution shift when it happens, so that they do something differently. Because if the distribution is not shifting, you don't need to update too much. But if it is shifting, just like Nyquist, right? What is a shift in this data distribution? It means at high frequency, and therefore you have to sample more there. This is kind of how I like to describe it. This is exactly the same thing with images with signals. If the signal drastically changes, then your Nyquist rate is higher because you have to sample more heavily to reconstruct the whole signal. And the same thing goes with data distribution. So there are papers that try to detect when a data distribution is shifting. And I know some papers use some ideas from signal processing to do that because they, yeah, anyway, yes, you're right. Those methods could be very interesting for this topic. I think there was a question before with the gentleman. No, behind. Yeah.
Oh,
okay. Because I saw his hand go up at the beginning.
Okay.
Just to be fair.
thank you very much for the talk. I really enjoyed it. I have a question regarding the real-time online continuous learning, because I was wondering about like the main question or main problem with that was that we don't have like the capability to just, like, for example, the example was that we can, like, there are 350,000 tweets per minute.
Yeah.
And we just can't like learn from all of these at the same time.
Correct.
Or at that rate. But the thing is that, like, isn't the even bigger problem that if we would have like a method to do that, that we would have to, because currently, if I understood everything correctly, we are learning from or we would learn from the labeled data that we get from like a previous like version of the machine learning algorithm or from the neural network. But wouldn't that lead to the problem that, for example, if like COVID starts, it doesn't know that COVID exists, then we get like the first tweets on it, and it's like things because there are just some people that are currently suddenly talking about a new virus. It would, for example, think that, oh, this doesn't exist.
Yeah.
But then we would, like you even said that earlier in the talk, that we would like train it on data that it labeled itself, and couldn't that do even like more damage to the whole thing than like helping if you could like in real time learn from.
Why would it damage? I don't
because it might like label all the COVID, like in that example, all the COVID.
It would predict, yeah. I mean,
yeah.
So let's say you had a model just before the COVID misinformation happens.
Yeah.
You had a model that was predicting misinformation. Once the COVID misinformation tweets came up, it would predict them wrong. Right? As the distribution shifts, right, there would be tweets about the misinformation of COVID. It would predict wrongly on them. But then there would be annotators, somebody in the Twitter sphere, right, taking these tweets and labeling them as misinformation. That goes to your continual learning model, and you will update your weights based on it. So in the next batch of tweets come out, it should be able to adapt to the distribution. You see? So
yeah, okay, but couldn't we then in the like at least in the first iteration, before someone can like really like change it and say that, okay, like COVID really exists and this is not like false information, couldn't like in the first few iterations, because of the sheer mass of data,
it would predict wrongly on the first few iterations, before the
like
new
damage itself in that way.
Oh yeah. Well, you mean because then it would become more like a problem of learning with noisy labels. That's actually another machine learning subfield. How about if somebody gave you a data set where so that's a good point, actually. I hadn't thought about that. So you're saying in the meantime, while you're waiting for new labeled data.
Yeah.
No, wait. No, wait. So when the COVID misinformation tweets come in, you will predict with an old model. You will get them wrong. You will predict, but you won't update until you have new data that's been annotated for those COVID tweets. You're assuming that those COVID tweets would have been labeled by somebody as not formed, but no, you're having a human annotating these things. So we're assuming that the humans will be perfect. But anyway, but you have a valid point. It means there's a subfield of machine learning where if you had a data set where the training set is not perfect, meaning that maybe adversarially or by mistake, some data is incorrectly annotated. How do you get about doing that? There's a whole subfield of that. So, but that's a good point. That's a good point. Another point is, and this is actually a future work that we're doing. I'm assuming that you get your data and the annotation, the labels, if you're doing supervised learning, together at the same time. This is not necessarily right. You will see the tweet. You can see the tweet before some Twitter army or Twitter backend labels it as misinformation. So there's a lag behind the data and the label. So think of two streams. One is the raw data stream, tweets only, and the other one would be the annotation. And then the annotation stream would be lagging behind the raw data stream. That's a very realistic setup, actually. Let's say you're doing image classification. So I can capture images at a rate higher than a human annotates them, right? So there's going to be a lag in that stream too. That is not considered here, but in future work, that is going to be even a more realistic setup, where the raw data and the annotation streams are separate, and there could be a lag between them. What do you do in that case? You just wait until the annotation comes? Can you do anything in the middle? Yes, there's another subfield of machine learning called semi-supervised learning. So in some part of one part of the training set has labels, the other part doesn't have labels. What do? That's called semi-supervised learning. But anyway, so these are details, but that's a good point that you have. Maybe noisy label learning could be a result, or has to be considered in the continual learning setup. That's actually makes a lot of sense.
Thank you.
Thank you.
Any more questions?
My question is if it's feasible to use inference of the model to filter data that we want to take to training, or if that's too expensive.
No, not at all. Actually, if you look at it here, that's a good point, and there's some methods that try to do that. No matter what you do, even if you don't update your model at all, you have to infer. You know, there is a misinformation filter at Twitter. Every tweet that comes up has to be analyzed by it. It has to happen, right? This has to happen. So that means you will always get a predicted label. You will always get the predicted label at the rate of the data stream. Now, what you're saying is that how can we use that to tell? So here there's no link. So how do we use this prediction that you're going to do anyway to inform what you do with this?
Yeah.
There are some papers on that too, but yeah, that's actually a very interesting way to explore. You're going to have to do this gray thing anyway.
Yeah.
No matter what. Can you link what you do here to what you do here? Yes. Yes.
The model already knows this data. Why take
This is the subset or the family of papers that try to tell whether the data distribution is shifting or not. Like, if I'm doing well on this data already, or if I've seen it before, why do I need to update? I.e., do I need to update on every single thing in the data stream? Right. So that goes to that. Yes. But how do you do it? And yeah. Anyway, but that's a good point.
Thank you.
That's a good point.
Thank you for your talk. This static and continual learning sounds for me like you say that our world is black and white. Is it something between static and continual?
In between.
Yeah, maybe half static, half continual. And
No, I would say everything is continual, but depending on the rate. So, I mean, if your data stream is, it reveals to you all the data at once and it stops. That's continual, but it depends on the rate of how much it reveals to you.
Okay, in second half, as a mathematician, I was thinking that we are doing long time modeling of PDEs, which model our world.
Yes.
We always deal with multi-scale nature.
Right.
Hierarchy, it's very important, multi-level. But today in your talk, I never heard about multi-scale nature of data, multi-scale nature of methods.
It should be multi-scale of the stream itself. Right. So for us, maybe I'm missing the point, but if you have a stream, you're multi-scale, meaning like the rates of sampling, if I'm not mistaken. Maybe that's what you're talking about. Yeah, this is what I'm saying. It's an open field. We can. It would be nice to see if you can integrate multi-scale ideas into this. But how? But again, this is not about reconstructing or solving a PDE or reconstructing signal. It's about training on data through minimizing of a loss, so that it generalizes well. So it's a complicated function, right? It's not your typical PDE, but maybe if you can model it as a PDE, there are, again, other papers from another realm where they try to model machine learning methods as PDEs or use machine learning models for PDE solvers. There's maybe if you model this as a PDE and then you use these types of methods, maybe. But you see, yes, the multi-scale is great, and it's still an early stage development of this whole field. So whoever can come up with really solid ideas for it will gain notoriety. But don't ask me on multi-scale because I don't know anything. I hear it from you guys all the time. I kind of understand it. It's like a course to find kind of thing. But how do you apply it directly here on the particular functions? There's an optimization happening in the middle. It has to be thought out. But yeah, maybe that's a solution or a solution.
I'm sorry, and also I didn't heard about compression of data. It was big data. Maybe it's compress them with different accuracy.
There's papers on that, and we actually have papers on that too. So especially for video. So what we've seen is that actually the methods that have a memory buffer, right? It's a number of bytes, right? You're restricted by the number of bytes. You can do whatever you want so long as you stay within those number of bytes. This is where compression gets into play. Now, when you do compressed video, do we just do MPEG compression or whatever? No, I mean, what we've shown is that actually in a video, you can compress it spatially or temporally, but you don't need the whole video. You can subsample remove many frames and keep the audio signal less compressed. And that's good enough to do continual learning. So like multimodal compression. So you sample, you compress the audio less than the video, right? Not with the same rates, and you use that to do continual learning instead. Yes.
Thank you very much.
But that's a good point. Compression is, of course, a big issue. But regardless of compression, no matter what you do, as you saw, it's about what you do at computation. When you update the model, if it takes you a long time to treat that compressed data, then you will have this issue, right? This issue of that a more computationally efficient method can do better than a computationally expensive method. So yes, the compression is about how do I fit more data into this memory buffer, okay? But that's like kind of complementary to the idea of how do you update the continual learning method itself. But there are papers on using compression and other purposes for the memory buffer. Actually, the papers that I mentioned to you, where the memory buffer is not meant to store past data, but it's meant to store the parameters of a network where you can probe it to generate the data of the past. That's actually goes to that. Like you compress it in a very different way. Anyway, but I think compression is definitely on the table.
Thank you.
Any more questions?
Hi, thanks for the talk.
Thank you.
I was wondering, so in the end, you kind of said that it's a sampling problem. So we're not using, so these more complicated models, like in this picture, they're not using enough data. But how are you sure that it's just not enough gradient steps, for instance?
No. Remember what I said, right? So a part of it is sampling. So if the data stream rate, okay, is treated independently. So if you have a computational method that is expensive, update method, continual learning method that's expensive, it's, let's say, 2 or 3 or 4 times slower than the data stream, then it becomes a sampling problem. It's not seeing the data, enough of the data. But then I told you about that experiment that we ran where it saw the data, but it only uses one gradient step to update, while the cheaper ones can do more. And still you get a similar plot. So it's not only about sampling, right? But in the real world, okay, just bottom line, 350,000 tweets per minute. And ERM, which is the most computationally efficient method that we have right now, is slower than that. So whatever you do, there's going to be a sampling issue, right? So I think the methods that try to sample in a smart way are valid, regardless, because a lot of the real world streams that we have are much faster than any computationally efficient method that we have right now, right? But it's not only sampling. There's other issues at play. So this idea of doing multiple iterations is what I mentioned, that in the time that you have, you can do one iteration or multiple ones. And in that case, you still get a similar kind of ordering here.
Okay, so in the first experiment, it was less data, but more iterations of gradient descent?
No, so okay, okay, let me recap. In the first experiment, the data stream is at its natural rate, okay? The ERM, which is the most computationally efficient method, right, is at the same rate as the data stream, okay? So with one iteration, okay? It can do one iteration. The computationally expensive methods are 2, 3, 4, 5, 10 times slower than ERM. In the second experiment, we artificially slow down the data stream so that it is the same rate as the slowest computationally expensive continual learning method to do one iteration, right? So like a one iteration is the baseline. Like how much time does it take you to do one forward-backward pass? If you know about deep learning, i.e. Infer and then estimate the gradient, like one gradient step, okay? And use that to determine the rate of, or the relative rate with respect to the data stream. So the first experiment, the ERM is as fast as the data stream, everything else is slower to do one iteration. And the other one, the data stream is slowed down to the slowest continual learning method that uses one iteration. ERM is allowed to do more than one iteration to do something with its time while it's waiting.
Okay, thanks.
I think there was one question up there, and we'll call it after that.
Thank you very much for the talk.
Thank you.
Very interesting. I have one question about the labeling, actually, because when you think about data coming in much increasing speed, wouldn't
wouldn't it be time to neglect labeling at all, to not miss something and go for something like some reinforcement learning kind of approach, so that the machine itself with some interaction decides by itself which are the right ones, for instance in the Twitter case, and which not? Is there some research on that in continuous time?
I don't know if I got the question. You're saying if the data stream is so fast, maybe you don't need to use the labels? Is that what you're saying? Or
the problem, it seems that from your explanations, it seems that the bottleneck is the human labeling of data, which
no, I mean, well, depending on the task. So for example, this task here, you get the label with the raw data, the image, instantaneously, because you're uploading, right? You take a picture, it's geotagged, uploaded to Flickr, Facebook, Instagram, whatever, you get the label for free. For the other, for instantaneously. For the other ones where you're annotating, for example, bounding boxes and images or misinformation tagging or whatnot, yes, there's a lag for that. So it depends on the task. By the way, there's something called continual self-supervised learning. Self-supervised learning is what was used to do GPT, right? So how do you do that continually?
that was actually,
That's your point.
That's what the question was about.
There are papers on continual self-supervised learning, where we have some work on that. What about continual federated learning or federated continual learning? Also, that's important, because if you're in a federated sense, you know, each device is continually getting a stream, but you're not allowed to see all the streams at once. So how do you do federated continual learning? Yeah, there are papers on that. But in the end of the day, if I'm building a misinformation classifier, right, it's a supervised task. So I need to wait for the labels, right? Somebody has to tell me. But like, as I told your colleague, in those cases, you're waiting for the human to annotate for you. But you're getting the data before. You get to see the tweet before it's annotated. Do you just assume that I only see the data when its annotation comes in? Or can I do some semi-supervised learning? Like when the tweet, before its annotation comes in, I can learn from the tweet itself in a semi-supervised way. And then when its annotation comes in, it becomes supervised. And that's something that we're exploring. If there's a lag between the annotation rate and the actual raw data stream rate. But in some cases like this, your raw data and annotation come in instantaneously. So it's task independent, it's task dependent. And for unsupervised learning tasks, like self-supervised learning, we're working on that too, to try to do it continually. Actually, one thing before we go, and that's a great point. So, and once Shaheen 3 comes here, I would like to test it myself. Okay, so did you guys know, guys and gals, know that when so ChatGPT or these GPT, they put together a static data set that's humongous, right? As far as we understand from what they disclosed to us, they did not do more than one epoch on this data. It means that they never saw the same data element more than once. There's some data they didn't even see because there's so much of it. So this is the proposition here. If that's the case, it kind of looks like a continual learning stream, right? So they had all this massive data and they never saw it again. In continual learning, you never see the data again. You just see it once and it gets thrown away, or you maybe put it in memory. So when these GPT or ChatGPT, whatever models were trained on this massive amount of data, and they're not doing another epoch, which means that they go back and see the data again, then it's like continual learning, but they're doing simple transfer, like sequential fine-tuning, which we know has catastrophic forgetting. So maybe, and this is why I want to test it, but we need Shaheen 3 for that. When this thing was trained on these billions of tokens, maybe in the first 100 million, it was learning something. The next 100 million, it forgot some from the past, and the new stuff was used to remember it and then improve a little bit more. And then, that's what happens as you go. So it could be that it's forgetting, remembering, forgetting, remembering, forgetting, remembering, and this is why it's so data hungry. So could you train a GPT with much less data if you did it in a continual way? That would be interesting. So But again, letting you know a factoid, which is we believe, we don't know for sure, we believe that they didn't even finish one epoch, meaning they never saw the data more than once. So maybe they are forgetting, and you know, if they did, if we can show that when we have chain 3 that if we can train this GPT in a continual way, you could do it with less data, more efficiently, or you can get better performance. Because the idea of forgetting is that you forget the past, and therefore new data coming in is needed to remember the past, right? So, but if you don't forget the past, maybe your performance keeps on going up, and it'll be better than the GPT that we have right now with the same amount of data. That would be cool to try out. We need chain 3 for it, though. All right. I hope that was. Did that get to your point?
Thank you very much.
Great. Thank you. So thank you for the invitation again. Thank you, Raul, for, I don't know if you're still there. And I hope you the best for the rest of the workshop. And if anybody has ideas about multi-scale simulation, filtering, whatever you guys are experts in for this idea of data distribution shift that can maybe be integrated here in continued learning, please reach out. We welcome you, and maybe we can write a paper together. All right. Thank you.